Good evening and welcome. Settle into whatever position feels easiest for your body right now, as if you're letting gravity do the work for you. If you can, let your jaw loosen a little and let your shoulders fall into a softer place. Welcome to Sleepy Science Universe. Take one slow breath in through your nose and a slow breath out. Let the exhale be just a little longer than the inhale, and notice how your chest and neck can unclench with it. If you'd like to, you can gently like the video or subscribe in that quiet way that helps these calm stories find the people who need them. No pressure at all, just a small, sleepy chi. Tonight we begin quickly with the simple idea of what a moon is and how these small companions drift around their planets like patient lanterns in the dark. A moon is a natural satellite orbiting a larger body. It stays nearby because gravity keeps it, the same steady pull that keeps planets in their lanes. Around the giant planets, this can mean dozens to hundreds of moons, from big round worlds to tiny tumbling stones. A quiet fact: moons can be rocky, icy, or mixed inside. Their makeup often reflects where they formed, like ingredients gathered from different parts of the early solar system. Beyond a boundary scientists call the frost line, ice becomes much more common because the cold makes water and other volatiles freeze and stick. One more gentle truth: gravity shapes big moons into round worlds. When a body is large enough, its own weight slowly pulls high spots down and pushes low spots up until it becomes nearly spherical. That rounding tends to happen when a moon reaches a few hundred kilometers across, roughly in the 400 to 600 kilometer range. In the background, a moon's orbit can be circular or stretched. A stretched orbit means the moon's distance changes as it goes around, sometimes by a noticeable amount. Scientists call that stretch eccentricity, and even a small eccentricity can change tides from gentle to stronger, like a quiet squeeze that repeats, a small step forward. Many moons spin as they orbit their planet. Over long times, the planet's gravity can slow that spin to guide it into a familiar pattern. This is tidal locking, and it can take millions of years until one side of a moon turns toward its planet again and again. A softer detail: tides can act like brakes on spinning moons. Gravity pulls unevenly on the near side and far side, and that slight difference can create friction inside the moon. Energy isn't lost, it's traded, often turning motion into internal warmth and slow orbital changes. And for one sleepy soul, that's enough to rest. Just for a moment. A moon's surface gravity is usually gentle. If you stood on our moon, you would weigh about 1/6 of what you weigh on Earth, because the moon's mass is smaller and its pull is softer. It's a kind of lightness that would change the way a single step feels. Farther out, some moons have almost no air at all. With low gravity and cold temperatures, gas particles can drift away into space instead of staying put. The escape speed is much lower than Earth's, so a thin atmosphere can vanish over time, leaving sharp stars in a clean, airless darkness. Closer in, other moons have real atmospheres that move. Even in deep cold, gases like nitrogen and methane can gather and swirl, forming winds, haze, or slow clouds. A moon can feel active and weathered, even when sunlight is weak and far away, if you drift a little. Moons often have cratered records of impacts. Without rain, rivers, or thick air to erase them, craters can remain for billions of years like quiet stamps in stone. When you look at a heavily cratered surface, you're often looking at a history book written in circles with that in mind. Some moons are constantly resurfaced. Heat from tides, slow ice flow, or volcanic activity can smooth away craters and replace old terrain with new. In some places, Scientists estimate the surface could be younger than 100 million years, which is young on a solar system timescale. Here's a calm surprise. Moons can also shepherd rings and shape them. A small moon's gravity can guide countless ring particles into sharp edges, ripples, and gaps. In some rings, those gaps sit where orbital resonances repeat, like a gentle rhythm that keeps clearing a lane. And for one sleepy soul, that's enough to rest. Slowly we notice a moon's day can be very long. If a moon spins slowly, sunlight can linger for days, or even for Earth weeks before night settles in. On a tidally locked moon, day and night can feel less like a quick cycle and more like a drawn-out tide of light. A quiet fact: moons can orbit in the same direction as their planet spins. That's called a prograde orbit, and it often suggests the moon formed from the same spinning disk of material that built the planet. In many systems, prograde moons cluster close to their planet, like children staying near a warm fire. One more gentle truth: some moons orbit backward around their planets. That backward path is a retrograde orbit, and it can hint that the moon didn't form there at all. It may have arrived later, a visitor captured by gravity, moving the wrong way through the family. In the background, moons can be grouped into regular and irregular families. Regular moons usually orbit close in orderly, nearly circular paths near the planet's equator. Irregular moons are often distant and tilted, sometimes at steep angles, as if they were caught rather than born there. A small step forward. The biggest planets tend to have the most moons. More mass means a stronger gravitational reach, and more room for stable orbits. In our solar system, Jupiter and Saturn dominate this count, hosting rolling collections that can feel like miniature systems of their own. A softer detail: some moons are probably broken fragments. When objects collide, they can shatter, and the pieces can settle into similar orbits, like a family made from one ancient impact. Astronomers recognize these families by shared distances, inclination, and orbital styles. Just for a moment, moons can tug on each other in repeating rhythms. These patterns are called orbital resonances, and they sound complicated, but the idea is simple. Timing matters. In a 2-to-1 resonance, for example, one moon makes 2 orbits in the time another makes 1, and that repeatable meeting creates a steady gravitational nudge. And for one sleepy soul, that's enough to rest. Farther out, resonances can keep a moon's orbit stretched. That stretching means tides never fully relax, so the moon flexes again and again, and that flexing can generate heat inside, not from sunlight but from motion, like a slow kneading that warms the interior. Closer in, moons can help stabilize a planet's tilt. Earth's moon plays this role for us, damping the wobble of Earth's spin axis over long spans of time. That steadiness helps keep seasons from swinging too wildly, a quiet contribution from a companion 384,400 kilometers away. If you drift a little, moons can also be temporary visitors. Sometimes a small object can be captured for a short while, looping around a planet for months or years, and then escape again. It's a reminder that orbits can be both stable and delicate, depending on the exact dance of energy. With that in mind, tiny moons can be only a few kilometers wide. At that size, they're closer to mountains than worlds, and their gravity is so weak that loose material can drift easily. Some are under 10 kilometers across, dark, tumbling pebbles that still count as moons. Here's a calm surprise. Moons show us how gravity builds structure. Many body systems may look complex, but they often organize into elegant patterns that can last for billions of years. A moon's quiet orbit is the visible trace of invisible forces doing patient work. And for one sleepy soul, that's enough to rest. Slowly, we notice. Earth's moon is our nearest large space neighbour. It's close enough that your eyes can follow its phases without any tool at all. On average, it orbits about 384,400 kilometres away, a distance that still feels intimate in the scale of space. A quiet fact: the moon is tidally locked to Earth. The same lunar face points toward us as it turns, so we always see the same broad pattern of dark plains and bright highlands. That synchronization matches a rotation period of about 27.3 days, the same time it takes to orbit Earth once. One more gentle truth: the moon's phases come from sunlight angle. The moon isn't changing shape. Our view is changing as it moves around Earth. The full cycle from new moon to new moon lasts about 29.5 days, and each phase is simply a different slice of sunlight on the same globe. In the background, the moon's surface is covered in fine dust. Tiny impacts from micrometeorites over immense time grind rock into powder called regolith. Some grains are sharp-edged because there's no wind or water to round them, and that dust can cling like soft ash. A small step forward, lunar seas are ancient lava plains. They look smooth and dark from Earth, which is why early observers called them Maria, but they're basalt rock, not water. Many of these lava flows formed roughly 3 to 4 billion years ago, when the moon's interior was warmer and more active. A softer detail: the moon's near side has more large lava plains. The far side, which we rarely see from Earth, is more heavily cratered and has fewer broad dark basins. One reason may be differences in crust thickness, varying by tens of kilometres, which made lava more likely to flood one side than the other. And for one sleepy soul, that's enough to rest. Just for a moment, the moon's gravity raises tides on Earth. Water bulges slightly toward the moon on the near side and slightly away on the far side, creating a slow repeating rise and fall. The timing is gentle and regular, with a common tidal cycle of about 12.4 hours between high tides. Farther out, the sun also helps make tides. Solar gravity adds its own smaller pull, and sometimes it aligns with the moon's pull, and sometimes it partly cancels it. When they align, spring tides are stronger. When they offset, neap tides are weaker, like two quiet hands pushing together or apart. Closer in, tides slowly move energy from Earth's spin. The friction of moving water and flexing ground steals a tiny bit of rotational energy, so Earth's rotation slows by a sliver. Over long times, the length of a day increases by milliseconds per century, small enough to ignore in daily life, but real on the scale of ages. If you drift a little, the moon is slowly drifting away from Earth. Scientists can measure this with remarkable precision using laser reflectors left on the moon, watching the light return and timing it carefully. The average increase is about 3.8 centimeters per year, the width of a fingernail spreading into space. With that in mind, the moon likely formed from a giant impact. Early in Earth's history, a Mars-sized body, often nicknamed Theia, may have collided with Earth, throwing debris into orbit. That debris gathered and cooled into one large moon, turning a violent event into a long, quiet partnership. Here's a calm surprise. The moon's surface records Earth's early era. Earth's weather and plate tectonics erase many ancient scars, but the moon keeps them almost unchanged. When you look at lunar craters, you're seeing preserved deep time, a calm archive written in stone. And for one sleepy soul, that's enough to wand. A quiet fact: lunar eclipses happen when Earth shades the moon. The moon slips into Earth's shadow and the bright disk dims, sometimes deepening into a coppery red as sunlight filters through Earth's atmosphere. A total lunar eclipse can last over an hour in totality, with the darkest part of the shadow moving slowly across the lunar face. One more gentle truth. Solar eclipses happen when the moon covers the sun. From the ground, our moon and the sun look almost the same size in the sky, even though the sun is vastly larger, because it's also vastly farther away. Their apparent widths are both around half a degree, which is why a small nearby moon can briefly hide a huge distant star in the background. That perfect fit is a temporary coincidence. The moon's orbit changes over long spans of time, and Earth's rotation changes too, so eclipse geometry slowly evolves. Over millions of years, the style and frequency of eclipses shift like a slow clock changing gears, one tooth at a time, a small step forward. The moon has water ice in some shadowed craters. Near the lunar poles, certain crater floors never see sunlight, and temperatures can stay below about 100 Kelvin, cold enough to trap ice for extremely long times. These cold traps hold a kind of frozen treasure in perpetual darkness, a softer detail. Lunar rocks tell a story of volcanic history. Samples brought back by astronauts show that lava once flowed across large regions of the moon, cooling into basalt plains. Many of these basalts date to roughly 3.1 to 3.8 billion years ago, a reminder that the quiet moon once had a warmer interior. Just for a moment. The moon's maria are smoother than highlands. Lava-filled low basins and spread out into wide, flat sheets, sometimes piling up to thicknesses of kilometers before cooling. That gentle smoothness is why the dark plains look calm even from far away, and for one sleepy soul, that's enough to rest. Farther out. The moon has moonquakes. Some are caused by tidal stresses, as Earth's gravity subtly flexes the moon, and others come from the slow cooling and shrinking of lunar rock. A few recorded moonquakes can last many minutes because dry, rigid ground doesn't damp vibrations the way Earth's wetter crust does. Closer in, the moon's temperature swings are extreme. With no thick atmosphere to spread warmth around, the surface can heat to about plus 127 degrees Celsius in sunlight and drop to around minus 173 degrees Celsius in darkness. The boundary between light and night can feel like a sharp line, a place where warmth ends and cold begins, if you drift a little. The moon is a baseline for other moons. It gives us a familiar size and mass for comparison, a reference point we carry as we travel outward in our minds. Its diameter is about 3,474 kilometers, a scale marker that helps other worlds feel more understandable. With that in mind, moons can form in disks around young planets. In the early solar system, planets likely gathered material in swirling, flattened clouds, and some of that material circled long enough to clump into moons. These disks can last millions of years, long enough for gravity to quietly sort dust into larger bodies. Here's a calm surprise. Moons can form from impacts too. A collision can throw debris into orbit around a world, and if that debris stays rather than falling back, it can gather into a companion. This same basic idea can happen around dwarf planets as well, where a single big impact can create a small moon system. Slowly we notice moons can be captured objects from elsewhere. A passing body can be caught if it loses enough energy, through interactions with gas, collisions, or the gravitational pull of multiple bodies at once. Capture is a delicate process, like threading a needle in motion, and when it happens it can leave a moon on a tilted or backward path. And for one sleepy soul, that's enough to rest. Now, just for a little while, you can let your breathing become the quiet background music. Inhale and exhale, and then inhale again as slowly as you can manage, and let the exhale take its time. We've noticed what moons are, and how gravity holds them, and how our own moon gives us a calm baseline. We've drifted through phases and eclipses, through tides and timekeeping, and even through ice hiding in permanent shadow. If any detail feels too bright in your mind, you can let it dim, the way a cratered surface softens at night. You don't have to keep the numbers. You can let them float past like dim starlight, just enough to feel the scale of things and then gone again, leaving only the gentle motion. A quiet fact. Many small moons look like potatoes in space. They're too small for gravity to pull them into a sphere, so they keep irregular, lumpy shapes. Some are only 10 to 200 kilometers across, tumbling through darkness like quiet stones. One more gentle truth. Some moons rotate in a chaotic way. Instead of spinning smoothly around one stable axis, their rotation can wobble and change over time, especially if they're oddly shaped and disturbed by strong gravity nearby. Hyperion, a moon of Saturn, is a famous example, turning in a way that's hard to predict far ahead. In the background, a moon can have a layered interior. Rock and ice can stack like a slow geological sandwich, and in some cases a layer of liquid water may sit between them. Scientists infer these layers from density and gravity measurements, which hint at what's hidden under the surface. A small step forward. Heat inside moons can come from tides. When a moon is stretched and squeezed by its planet's gravity, friction inside converts motion into warmth. This tidal heating is strongest near giant planets, where gravity is powerful and orbits can be tugged out of perfect circles. A softer detail. Heat can also come from radioactive decay. Certain elements in rock release energy as they slowly transform into other elements, and that trickle of heat can last for billions of years. It's a quiet internal ember, small but steady, especially in larger, rockier worlds. Just for a moment, some moons have magnetic signatures. If a moon contains a salty ocean, moving electrical currents in that water can create an induced magnetic field when it passes through a planet's larger magnetic environment. Europa shows clues like this, where the measurements hint at conductive liquid layers below the ice. And for one sleepy soul, that's enough to rest. Farther out. Moons can have cliffs made of ice and rock. Low gravity allows tall features to stand without collapsing as easily as they might on Earth. In some places, scarps and steep walls can stretch for kilometers, casting long shadows that make the terrain feel sharply sculpted. Ocean. Crater chains can form from broken impactors. When a comet or asteroid fragments as it approaches, the pieces can strike in sequence, leaving a line of craters like beads on a string. These chains can extend across hundreds of kilometers, dotted signature of a single broken visitor. If you drift a little. Some moons are colored by sulfur or organics. On Io, sulfur and sulfur compounds stain the surface in bright tones, while on Titan, complex organic haze gives the sky and surface a muted orange-brown. Chemistry can paint a world without any need for plants, just reactions unfolding in cold and time. With that in mind, many moons have leading and trailing hemispheres. The leading side faces forward in the moon's orbit like the windshield of a moving car, and it often takes more tiny impacts. Over time, that can subtly change surface texture and brightness, leaving a forward face and a following face with different histories. Here's a calm surprise. Tiny moons can sit inside rings. Their gravity can open narrow gaps and keep them crisp, like a small boat parting calm water. Saturn's moon Pan, for example, lives in the Encke gap, a lane carved through the ring material by a small steady presence. Slowly we notice Roche limits set where tides can tear bodies apart. If an object comes too close to a planet, the difference in gravity between its near side and far side can exceed what the object can hold together. The exact distance depends on density, but the idea is simple. Too close, and gravity stops being a hug and becomes a pull in two directions. A quiet fact: rings can be made of moon fragments. If a moon breaks apart near a planet, the pieces can spread into a thin disk. Ring particles can range from dust-sized grains to chunks the size of boulders, all orbiting together in a bright, delicate band. One more gentle truth: a planet's tilt can shape moon orbits over time. The planet's equator defines a natural plane, and as the planet slowly precesses, meaning its spin axis traces a slow circle, moon orbits can be nudged and adjusted. These cycles can play out over thousands of years, quietly retilting the long-term dance. In the background, moons can migrate outward or inward. Tidal interactions transfer energy and angular momentum, and that can slowly move a moon's orbit. The rate can be tiny or noticeable depending on the system, but it's often a story told in millimeters, centimeters, and long patience. A small step forward, resonances can protect or destabilize orbits. When repeated gravitational tugs line up in timing, they can lock a pattern in place, keeping distances stable, or they can amplify changes. The Laplace resonance among Jupiter's large moons is a well-known example of timing creating structure. A softer detail: resonances can also fuel volcanism and oceans. When resonant tugs keep an orbit slightly eccentric, a moon keeps flexing, and that flexing makes heat. The linked rhythm of Io, Europa, and Ganymede shows how orbital timing can power both blazing volcanism and hidden water, and for one sleepy soul, that's enough to rest. Farther out. Moons can have polar regions colder than space feels. In some craters near the poles, sunlight never reaches the floor, so the cold can settle in and stay. Scientists call these places permanently shadowed regions, and temperatures can remain low enough for ice to survive for extremely long times. It's like a deep freeze pocket tucked into darkness. Closer in, a moon's surface can garden itself. Tiny impacts over millions of years churn the top layer the way a gentle rake might turn soil. On airless worlds, this slow mixing builds a regolith blanket that can be meters deep in places, made from crushed rock and glassy grains. The surface is quiet, but never completely still, if you drift a little. Some moons show fresh streaks from recent impacts. When an object hits, it can splash bright material outward in rays, like pale paint across a darker ground. Over time, radiation and micrometeorites darken those rays, so their brightness hints at relative youth, sometimes on the order of tens of millions of years. In a calm way, even brightness can be a clock. With that in mind, moons can help us test planetary formation theories. Each planet's moon system is like a different case study in the same physics, shaped by local conditions and long time. We have 8 planets, but far more moon histories, each one showing a different way matter can gather, break, and gather again. Here's a calm surprise: Io is the most volcanically active moon we know. Jupiter's gravity, plus the repeated tugs from neighbouring moons, flexes Io so intensely that its interior heats and melts. Spacecraft have observed hundreds of active volcanic centres, with plumes that can rise high above the surface like brief glowing breaths. Even in darkness, Io is alive with heat. Slowly we notice, Io's sulfur paints its surface in vivid tones. Sulfur and sulfur compounds can frost the ground and stain it in yellows, reds, and darker browns, depending on chemistry and temperature. Pure sulfur melts at about 115 degrees Celsius, and mixtures can behave differently, which is why Io's colours shift from place to place. And for one sleepy soul, that's enough to rest. A quiet fact. Europa is an icy moon with a fractured shell. Its surface is threaded with long lines and broken plates, suggesting the ice has moved, cracked, and refrozen many times. Scientists estimate Europa's ice shell could be tens of kilometers thick, though the exact thickness depends on how the heat and ice flow are modelled. The surface looks like frozen motion. One more gentle truth. Europa likely hides a global salty ocean. Tidal flexing can provide internal heat, and salt lowers the freezing point of water, helping liquid remain stable under ice. Some estimates place the ocean's depth around tens to roughly 100 kilometers, though the precise number is still debated. Under that quiet shell, the idea is simple. Water may be waiting in the background. Europa's surface is relatively young. When scientists count large craters, there simply aren't many, which suggests resurfacing has erased older impacts. In some regions, the surface may be under 100 million years old, and possibly much younger in spots. A young surface in space is a sign of ongoing change, gentle but persistent. A small step forward. Ganymede is the largest moon in the solar system. It's wider than Mercury, even though it has less mass overall because it contains more ice. Its diameter is about 5,268 kilometers, making it feel planet-size when you compare it to familiar worlds. In the dark, it's a large globe with a quiet, icy face, a softer detail. Ganymede has its own magnetic field. That means it likely has a moving, electrically conductive layer inside, often modelled as a liquid iron-rich core, generating magnetism the way Earth does. It's still the only moon we know with an intrinsic magnetic field, a rare kind of hidden engine. Magnetism can be an invisible signature of a living interior, just for a moment. Callisto is heavily cratered and ancient-looking. Its surface holds a dense record of impacts, as if time mostly wrote on it rather than erasing it. Many scientists consider its surface among the oldest in the solar system, near 4 billion years old. On Callisto, the past stays close to the surface, and for one sleepy soul, that's enough to rest. Farther out, Callisto may still have an ocean deep down. Magnetic measurements and models suggest a conductive layer could exist beneath the ice, which would fit with a salty ocean hidden far below. If it exists, it might sit tens of kilometers beneath the surface, sealed away from the cratered skin like a secret reservoir. Even a quiet, old world can keep something liquid inside. Closer in, Jupiter's big moons are locked in a resonance chain. Their orbital periods form a repeating rhythm, especially among Io, Europa A, and Ganymede. The pattern is often described as 1 to 2 to 4, meaning Europa orbits once for every 2 orbits of Io, and Ganymede orbits once for every 2 orbits of Europa. Timing here becomes a source of heat. If you drift a little, Jupiter has many small irregular moons far out. These moons often have tilted orbits and can travel millions of kilometers from Jupiter, where the planet's pull still holds them, but the paths feel less orderly. Many are likely captured objects, and their distant, uneven lanes suggest a wilder origin. Far away from the bright disk, small companions still circle, with that in mind. Irregular moon groups share similar orbits. When astronomers see multiple moons with matching inclinations and distances, it hints that they might be fragments of a larger body that broke apart long ago. Families like the Ananke group or the Calm group are examples of these clustered patterns. Even after a collision, gravity can keep the pieces in a recognizable family. Here's a calm surprise. Some Jovian moons are only a couple kilometers wide. At that scale, they're not round at all, and their gravity is so weak that a tossed pebble could drift for a long time before coming down. Many are in the 1 to 5 kilometer range, tiny enough to be invisible without careful telescopes. And still, they count as moons, small slender companions. Slowly we notice Jupiter's strong radiation affects nearby moons. Charged particles trapped in Jupiter's magnetic field can strike surfaces, altering ice and rock by breaking molecules and creating new compounds. The radiation belts near Jupiter can be intense, especially for moons that orbit close in. Invisible particles can weather a world as surely as wind does on Earth. And for one sleepy soul, that's enough to rest. A quiet fact: Europa's surface may exchange material with its ocean. Cracks and ridges could allow salts and other materials to move upward, and surface oxidants created by radiation might slowly mix downward if pathways exist. Some studies have searched for hints of plumes or venting, but the evidence is still debated. The calm truth is that we're still learning how open Europa's shell really is. One more gentle truth: Ganymede's ice shows grooves and bands. Long, parallel ridges and troughs cross parts of the surface, suggesting ice tectonics, slow, brittle cracking and gentle flow, reshaped wide regions. Some grooved terrain stretch for hundreds of kilometers, like careful comb marks in frozen ground. The surface can look organized, as if stress drew straight lines in the background. Callisto's surface has multi-ring impact basins. One famous example is Valhalla, a huge structure with concentric rings that spread outward like ripples on a pond. These rings span thousands of kilometers across, implying an impact so large it reshaped the crust in waves. On an airless world, ripples can last for ages. A small step forward. Some Jovian moons may have dirty ice. When ice mixes with darker rock and dust, the reflectivity changes and the world can look mottled, matte in one region, brighter in another. Astronomers measure this with albedo, a simple way to describe how much light a surface reflects. Even without colour, brightness differences tell a story. A softer detail: Jupiter's gravity can capture comets that then collide. The planet's immense pull can alter a comet's path, sometimes breaking it apart and guiding fragments inward. The Shoemaker-Levy 9 impacts showed this dramatically, when fragments struck Jupiter and left dark scars that lingered for days to weeks. It was a reminder that giant planets can shape the traffic of the solar system, just for a moment. The Galilean moons form a mini-system around Jupiter. 4 large worlds, Io, Europa, Ganymede, and Callisto, offer a range from fiery volcanism to hidden oceans to ancient crater fields. Their sizes range from about 3,100 kilometers across for Io to over 5,200 kilometers for Ganymede, like a small set of planets orbiting one planet. And for one sleepy soul, that's enough to rest. Farther out. Io's lava lakes can be hotter than many Earth eruptions. The glowing flows suggest silicate lava that can reach temperatures above about 1,000 degrees Celsius, sometimes significantly higher depending on composition. In the darkness, those hotspots are like tiny furnaces on a cold world, brief points of brightness on a surface otherwise shaped by sulfur frost. Heat can exist in surprisingly small places, closer in. Europa's ice may have ridges like frozen waves. Repeated cracking and refreezing can push material upward, building raised lines that braid and cross over each other. Some ridges rise meters to tens of meters high, stretching across long distances like a quiet frozen shoreline. Even without liquid at the surface, the ice can look restless, if you drift a little. Ganymede's surface mixes old dark and newer bright regions. Dark terrain looks older and more heavily cratered, while brighter grooved regions may have been resurfaced later by tectonic processes in ice. The contrast can be striking. like a patchwork quilt stitched from different eras. It's a reminder that a single world can carry multiple chapters side by side, with that in mind. Callisto orbits farther out, in calmer tides. Being more distant from Jupiter means it experiences less gravitational stretching, so tidal heating is weaker than it is for Europa or Io. Less flexing usually means less internal warmth, and that can help explain why Callisto's surface looks older and less reworked. Distance in space can be a kind of quiet. Here's a calm surprise. Jupiter's moons teach us how tides sculpt worlds. Internal energy doesn't have to come from sunlight, it can come from motion and repeated flexing converted into heat over immense time. In some cases, tidal power can rival or exceed other heat sources, shaping geology from the inside out. A world can be warmed by the way it moves. Slowly we notice Saturn's rings are made mostly of water ice. The particles reflect sunlight like powdered snow, even though each piece is just a tiny body following its own orbit. The sizes range from dust grains to chunks as large as meters, all spread into a thin, bright disk around the planet. And for one sleepy soul, that's enough to rest. A quiet fact. Saturn's moons interact with the rings constantly. Their gravity makes ripples, waves, and sharp edges, shaping patterns that drift through the rings like slow music. In the densest parts, spiral density waves appear, compressions that travel through the ring material caused by resonances with nearby moons. One more gentle truth. Enceladus is a small moon with powerful geysers. Jets of water vapor and icy particles spray from fractures near its south pole, escaping into space in shining arcs. Enceladus is only about 504 kilometers across, small enough to seem unlikely as an active world, and yet it produces one of the most dramatic plume displays we've seen, in the background. Enceladus likely has a salty ocean under its ice. The plume material contains clues, salts, tiny grains, and compounds that suggest liquid water interacting with rock below the surface. The simplest picture is an ocean hidden beneath an icy shell, warmed by tides and venting through cracks like a quiet pressure release. A small step forward, Enceladus feeds Saturn's E-ring. The particles ejected from its geysers don't just vanish. Many spread out and form a wide, faint ring that wraps around Saturn. The E-ring spans hundreds of thousands of kilometers, so a small moon can supply a structure vast enough to dwarf the planet itself. A softer detail. Titan is Saturn's largest moon. It's slightly bigger than Mercury and wrapped in a thick haze that hides its surface in visible light. Its diameter is about 5,150 kilometers, and in the telescope it looks like a soft, muted globe with a blurred edge. Just for a moment. Titan has a thick nitrogen atmosphere. It's the only moon in our solar system with dense air, and the pressure at its surface is about 1.5 times Earth's surface pressure. That means if you could stand there safely, the air would press on you with a steady, heavy quiet, like being under shallow water, and for one sleepy soul that's enough to rest farther out. Titan has lakes and seas of liquid hydrocarbons. The cold is deep enough that methane and ethane can collect on the surface in dark pools, reflecting dim sunlight like mirror ink. Typical temperatures hover near minus 179 degrees Celsius, so water ice behaves like rock, while methane can play the role of water. Closer in, Titan's methane works like a weather cycle. It can evaporate, rise, condense into clouds and fall as rain, carving channels and filling basins over time. Clouds and rainfall have been observed, meaning Titan has a kind of slow alien hydrology, familiar in pattern, but made of different materials if you drift a little. Saturn's moon, Mimas, has a giant impact crater. The Herschel crater is about 130 kilometers wide, and it gives Mimas a striking appearance like a single large eye staring outward. For a moon only about 396 kilometers across, that crater is enormous, suggesting the impact nearly shattered the moon. With that in mind, Iapetus has a dramatic two-tone surface. One hemisphere is much darker than the other, creating a sharp contrast that stands out even in older telescope observations. The brightness difference is extreme, as if one side has been dusted with soot while the other stayed clean ice. Here's a calm surprise. The dark coating on Iapetus may come from dust. Material from outer, darker moons can drift inward and preferentially settle on the leading side of Iapetus, the face that meets the oncoming dust. Over time, this creates a dark mask that absorbs more sunlight, which can even encourage further darkening by warming and moving surface ice. Slowly we notice Rhea is a large icy moon with a cratered face. Its surface looks quiet and ancient, with impacts preserved in pale ice. Rhea's diameter is about 1,528 kilometers onwards, making it a substantial world, large enough to feel like a planet's moon in the fullest sense. And for one sleepy soul, that's enough to rest. A quiet fact: Dione has bright, wispy fractures. Long, reflective cliffs and cracks trail across parts of its surface, catching sunlight and standing out against darker ice. These fractures can extend for hundreds of kilometers, suggesting deep stresses that once pulled the crust apart. One more gentle truth: Tethys has a huge canyon system. Ithaca Chasma stretches roughly 2,000 kilometers, nearly 3/4 of the way around the moon. A canyon that long implies a major cracking event, perhaps tied to internal changes or impacts, leaving a seam-like scar across a pale surface. In the background, some Saturn moons are Trojan companions. They share an orbit with the larger moon, staying ahead or behind at stable points where gravity balances. These places, called L4 and L5 points, are like gentle eddies in orbital space where small bodies can rest, moving in step without colliding. A small step forward, Pan and Daphnis sculpt ring edges up close. As they orbit within gaps, they tug on nearby ring particles and raise waves along the gap boundaries. The wave crests can reach heights of kilometers, which is surprisingly tall for a structure made of loose ice grains, all shaped by one small moon's steady passage. A softer detail: Phoebe is a dark, irregular moon far out. It orbits Saturn in a retrograde direction, which strongly suggests it was captured rather than formed in place. Phoebe is about 213 kilometers wide, and its dark surface resembles objects from the outer solar system, like a piece of distant darkness brought close, just for a moment. Phoebe's dust can feed a huge faint ring. The Phoebe ring is enormous, stretching millions of kilometers, yet it's extremely thin and dim, made of sparse dust grains. It's a reminder that a ring can be vast and still nearly invisible, a ghost structure spanning space. And for one sleepy soul, that's enough to rest. Farther out, Hyperion rotates chaotically. Its irregular shape and interactions with Saturn's gravity keep its spin from settling into a simple rhythm. Over seasons, it can tumble in ways that make day and night patterns unpredictable, a slow corkscrew turning in the cold. Closer in, Hyperion's surface looks sponge-like. It's full of pits and cavities, and its density is very low, suggesting a porous structure, more like a rubble pile than a solid rock. Porosity can help absorb impact energy, which may contribute to its unusual texture, like a frozen coral of craters, if you drift a little. Titan's haze blocks visible light, but not all wavelengths. In infrared, there are windows where instruments can peek through the atmosphere and map the surface below. Cassini used these spectral windows to reveal lakes, dunes, and varied terrain, turning a blurred orange ball into a real landscape. With that in mind, Titan has dunes made of organic grains. Winds shape dark material into long dune fields that can stretch hundreds of kilometers, forming parallel ridges like soft waves. The grains are thought to be complex carbon-rich particles created in the atmosphere and settled onto the surface, becoming Titan's version of sand. Here's a calm surprise. Enceladus's south pole is unusually warm. Heat leaks out along fractures nicknamed tiger stripes, where the crust is broken and active. The warmth can be tens of degrees higher than surrounding regions, enough to help drive venting and keep pathways open beneath the ice. Slowly we notice Saturn's moons show a full spectrum of icy behaviours. From still ancient crater fields to active plumes and thick atmospheres, the range is wide and gentle to explore. Their sizes span from tiny ring-embedded moons to Titan's planet-like scale, and each one holds a different kind of quiet. A quiet fact. Icy ocean worlds are kept warm by tides and salt. When a moon is flexed by gravity, that motion becomes internal heat, and salt can help water stay liquid by lowering its freezing point. It's a simple recipe repeated in different ways: bending, warming, and water that doesn't want to freeze. One more gentle truth. Liquid water can exist without sunlight. Deep below an ice shell, warmth from tidal flexing or slow radioactive heat can keep water moving in the dark. On Earth, the idea of hydrothermal vents shows how heat and chemistry can support activity without any light at all. In the background, salty oceans conduct electricity. That's one reason magnetic measurements matter so much for these moons, because moving conductive water can respond to a planet's magnetic field. When scientists see signs of an induced magnetic signal, it can be a quiet clue that something salty and liquid is hidden below. A small step forward, plumes can sample subsurface oceans from afar. If cracks or vents connect to a deep reservoir, jets can carry tiny droplets and grains outward into space. On Enceladus, plume material can rise hundreds of kilometers above the surface, offering us a way to taste the interior without drilling. A softer detail. Ice shells can behave like slow rock. Over years to millennia, ice can creep, flow, and deform under stress, even while it looks rigid in a photograph. That slow movement can open fractures, close them, and reshape the surface in gentle time, just for a moment. Thin ice can flex more and heat more. A thinner shell bends more easily under tidal forces, concentrating stress along cracks and boundaries, which can create more frictional heating. In a quiet way, the thickness of an unseen ice layer can decide how lively a world becomes. And for one sleepy soul, that's enough to rest. Farther out, thick ice can still hide liquid layers. Pressure and internal warmth can keep water stable beneath a deep crust, even if the shell is tens of kilometers thick. When you picture it, you can imagine a long, silent lid of ice with a darker ocean resting underneath. Closer in, ammonia can help water stay liquid. Mixed into water, ammonia acts like antifreeze, lowering the freezing point so liquid can persist at lower temperatures. It's a simple chemical trick that may matter for some distant moons and small icy bodies. If you drift a little, ocean floors might be rocky, not icy. If liquid water rests on rock, chemical reactions can happen where the two meet, releasing energy and changing minerals. One candidate process is serpentinization, where water reacts with certain rocks and produces hydrogen, quiet chemistry that can carry energy into darkness. With that in mind, Europa may have chaos terrain from broken ice. Some regions look like plates that fractured, rotated, and refroze in a new arrangement, as if the surface briefly softened and then locked again. These areas can span tens to hundreds of kilometers, like a shattered mosaic spread across a globe. Here's a calm surprise. Ganymede may have multiple water layers. Deep inside, high pressure can form exotic phases of ice, different crystal structures than the ice we know on Earth. Scientists sometimes label these as Ice 3, 5 or 6, and they may create stacked layers of ice and water at depth, like a Hidnokishi texture. Slowly we notice Enceladus's plume grains contain salts and organics. Instruments detected tiny particles carrying chemical hints, suggesting water interacted with rock and dissolved minerals before escaping. Each grain is microscopic, but together they tell a large story about a small moon. And for one sleepy soul, that's enough to rest. A quiet fact: habitability needs energy, water, and chemistry together. A moon doesn't have to be warm on the outside to provide those ingredients inside. In these ocean worlds, the energy often comes from tides, the water from internal reservoirs, and the chemistry from rock, salts, and long reactions. One more gentle truth: radiation can modify surface chemistry on icy moons. Charged particles and ultraviolet light can break apart molecules in surface ice, creating new compounds like oxidants. It's a slow kind of chemical weather, invisible in motion but powerful over time. In the background, oxidants could drift downward over time. If the surface makes reactive compounds and some pathway eventually carries them into an ocean, that can provide chemical energy. The details depend on geology, how cracks open, how ice moves, and whether mixing is possible. So the idea stays gentle and uncertain. A small step forward, ice crusts can preserve traces like a freezer. Cold temperatures slow down many chemical changes, letting materials remain stable longer than they would on warmer worlds. In that way, an icy shell can be both a barrier and an archive, a softer detail. Some moons may have subsurface lakes, not global oceans. Instead of a single planet-wide reservoir, there could be pockets of liquid trapped between layers of ice. Scientists sometimes call these perched lenses, hidden water that rests in quiet places, waiting between cold layers, just for a moment. Ocean worlds remind us that warmth can be internal. A moon can look still from far away and yet be active beneath the surface, driven by flexing and chemistry. Internal heating can last billions of years in some systems, turning motion into a long, quiet fire under ice. And for one sleepy soul, that's enough to rest. Farther out, future missions target these moons for close study. Instruments like radar sounders, spectrometers, and particle analyzers can look for signs of structure and chemistry. The goal is simple: understand the layers, the energy, and whether the ingredients for lifelike chemistry are truly present. Closer in, even unanswered questions can feel calming. In planetary science, not yet measured is a real category, and it leaves space for curiosity without urgency. The unknown can sit gently beside the known, like darkness beside starlight. A quiet fact: Uranus has moons that orbit in a tilted system. Uranus is tipped on its side, with a tilt of about 98 degrees, so its equator, and the plane where many moons orbit, lies almost sideways compared to the rest of the solar system. It makes the whole system feel rotated, like a clock turned on its edge. One more gentle truth: Miranda has giant cliffs and patchwork terrain. Its surface looks like pieces stitched together, with abrupt boundaries and strange landscapes packed close. One dramatic feature, Verona Rupes, has been estimated at several kilometers tall, sometimes described as roughly 5 to 10 kilometers, making it among the tallest known cliff-like structures in the solar system. In the background, Ariel shows signs of resurfacing. Compared to some neighbours, parts of Ariel look smoother with fewer craters, hinting that internal activity once refreshed the surface. The exact history is still being pieced together, but the contrast suggests Ariel didn't stay frozen in one state forever. A small step forward, Umbriel is darker and more cratered. Its surface reflects less light than many of Uranus's other large moons, giving it a more shadowed look. That darkness can come from composition, radiation effects and age, different ingredients adding up to a quieter, dimmer face. And for one's sleepy soul, that's enough to rest. A softer detail, Titania is Uranus's largest moon. It shows long fault valleys and fractures, signs that the crust was pulled and cracked in the past. Titania's diameter is about 1,578 kilometers, large enough to hold a complex history, even if we've only seen it in brief detail, just for a moment. Oberon is another large Uranian moon with big craters. Bright ejecta around impact stands out against darker ice, like pale halos where material was thrown outward. Oberon's diameter is about 1,523 kilometers, placing it close to Titania in size, a paired set of quiet, cratered worlds. Farther out, Uranus's moons hint at past collisions and shifts. The early solar system was crowded and energetic, and big changes could happen quickly before settling into long calm. The heavy bombardment era left marks across many worlds, and these moons likely carry that era in their scars. Closer in, Neptune's moon, Triton orbits backward. A retrograde orbit around Neptune strongly suggests Triton was captured, not formed alongside the planet's regular moons. Triton is Neptune's biggest moon, and its presence may have reshaped Neptune's system after it arrived. A quiet fact: Triton has nitrogen ice and extremely low temperatures. With sunlight so weak at Neptune's distance, the surface stays deeply cold near about -235 degrees Celsius. In that cold, nitrogen can freeze like rock, forming frosty plains that still change slowly with seasons. One more gentle truth: Triton shows signs of active geology. Voyager 2 saw terrain that looked young and smooth in places, and dark plume-like features that suggested material had erupted or vented from below. Even far from the sun, an icy world can still move, crack and quietly release gas. And for one sleepy soul, that's enough to rest. A softer detail. Neptune also has small inner moons near faint rings. These moons orbit close to the planet in regions where ring arcs and dusty structures can appear and shift. Moons like Naiad and Thalassa are tiny, and their influence can be subtle, but they help shape the edges and patterns of the material nearby, just for a moment. Captured moons can reshape entire systems. When a large body like Triton is captured, it can disturb older moons, altering orbits, causing collisions or clearing the neighbourhood over long time. Models suggest Triton's arrival may have been disruptive, like a quiet reset of the system's earlier arrangement. And for one sleepy soul, that's enough to rest. Farther out, Pluto's moon system is a special case of balance. Pluto and Charon orbit a shared point in space, and that point, the barycenter, actually lies outside Pluto's surface. It means the pair behaves less like a planet and a moon, and more like two companions circling each other in a slow, steady loop. Closer in, tilted, captured and cratered moons show many histories. Across our solar system, moon doesn't mean one kind of place. It means a whole family of forms. Some are smooth and young, some are battered and old, and some are strangers that arrived late and stayed. If you drift a little, distant moons teach patience in observation. At the far edges of the solar system, even radio signals take hours to travel back, and images arrive as a slow stream of data. In a way, the distance builds its own calm, forcing science to move at the pace of light. With that in mind, Pluto and Charon form a near-binary pair. Charon is about half Pluto's size, and their mutual orbit gives the system a balanced feeling, like two stones tied together and spun gently. The scale is intimate for space and yet still vast, thousands of kilometers across, turning for silence. Here's a calm surprise. Charon's surface shows canyons and plains. Fractures and chasms stretch across long distances, and features like Serenity Chasma form a canyon system that hints at crustal stretching and internal changes. The lengths are immense in human terms, spanning hundreds of kilometers like a long crack in frozen ground. Slowly we notice Pluto has several tiny moons besides Charon. Nix, Hydra, Kerberos and Styx are small and faint, with sizes in the tens of kilometers range, more like irregular mountain-sized bodies than round worlds. They circle in the quiet space around Pluto, adding a small family around a distant pair. And for one sleepy soul, that's enough to rest. A quiet fact. Some small Pluto moons spin rapidly and oddly. In a system dominated by a binary pair, gravitational tugs can make tiny moons rotate in complex ways, sometimes changing orientation over time. Their spins can be quick and irregular, like tumbling lanterns that never fully settle. One more gentle truth. Dwarf planet Eris has a moon named Dysnomia. Even far beyond Neptune, gravity can hold companions, and small systems can form or persist in the cold. Dysnomia's orbit takes weeks, a slow and steady path around a distant icy world. In the background, Haumea has moons and a fast spin. Haumea rotates in about 3.9 hours so quickly that it's stretched into an elongated shape rather than a sphere. That rapid rotation is a reminder that not all worlds turn slowly. Some spin like a hurried clock hand even in deep space. A small step forward. Small body moons can form from gentle collisions. In the Kuiper belt, where many icy objects orbit, impacts can create debris that gathers into a companion rather than dispersing. Over time, even small gravity wells can organize a few pieces into a stable pair. A softer detail. Some asteroids have tiny moons too. These systems can look like pebbles orbiting pebbles with satellites only a few kilometers across. Despite their small scale, they offer clear lessons in orbital mechanics because the same gravity rules apply, just with softer pulls, just for a moment. Mars has two small moons, Phobos and Deimos. They are irregular in shape and likely either captured objects or fragments from an impact long ago. Phobos orbits Mars in about 7.7 hours so quickly that it rises and sets multiple times in a single Martian day. And for one sleepy soul, that's enough to rest. Farther out, Phobos is spiraling slowly inward toward Mars. Tidal forces are pulling it down over time, tightening its orbit. Models suggest it may break apart in tens of millions of years, possibly forming a temporary ring before the pieces fall to Mars. Closer in, Deimos orbits farther out and more calmly. It's smaller and more distant than Phobos, and it takes about 30.3 hours to circle Mars once. In that wider path, tides are weaker, and Deimos feels like a quieter companion, hovering at a distance, if you drift a little. Earth's moon is unusually large compared to its planet. The moon holds about 1/81st of Earth's mass, which is a high ratio compared to most planet-moon pairs in our system. That makes Earth and the moon feel like partners, not just a planet with a small follower. With that in mind, large moons can help planets keep steady seasons. By stabilizing tilt, a big companion can reduce how wildly a planet's axis wobbles over time. The details vary from system to system, but the idea is gentle. A nearby partner can smooth a planet's long-term motion. Here's a calm surprise. Captured moons often have tilted, stretched orbits. Their paths can look less neat than regular moons formed in place, with high inclinations and more eccentric shapes. This is one of the quiet fingerprints of capture, motion that doesn't fully match the planet's original rhythm. Slowly we notice, irregular moons can collide over long times. Even distant orbits can cross or interact, and over immense spans rare collisions can happen. Most of the time the space is wide and empty, but the possibility remains, a slow-motion billiards game played over ages. And for one sleepy soul, that's enough to rest. In the background, dust from impacts can coat other moons and rings. Tiny grains can be blasted off a surface by micrometeorites, then drift and settle somewhere else, like ash that never quite falls straight down. These particles are often only microns to millimeters in size, but over long time they can subtly change the color and brightness of a neighboring world. A small step forward, some moons may have subsurface oceans we haven't confirmed. The evidence can be indirect, small changes in gravity, hints in magnetic measurements, or surface features that suggest movement below. Often it's the combination that matters, gravity plus magnetism plus geology, all pointing in the same quiet direction. A softer detail, moons can be stepping stones for exploration. Their lower gravity can make landings and takeoffs less demanding than on a full-size planet. And their surfaces can preserve samples like a freezer preserves food. In a way, a moon can be both a destination and a calm platform for reaching farther, just for a moment. Moons hold clues to the early solar system's chaos. Their crater counts, tilted orbits, and broken families are all traces of a time when objects collided and migrated more often than they do now. Some of the oldest records on moons stretch back billions of years, holding the memory of that early crowding in silent stone. And for one sleepy soul, that's enough to rest. Farther out. Even tiny moons can teach big physics. A small body still follows the same gravitational rules as a large one, just with gentler forces and slower changes. It's the same equations, the same dance, simply performed on a smaller stage with softer steps, closer in. Spacecraft have mapped many moons up close. Flybys turn tiny points of light into landscapes with cliffs, ridges, craters and plains, and they do it in minutes or hours of closest approach. Missions like Voyager, Galileo, Cassini and New Horizons each added pages to the same quiet atlas, one pass at a time, if you drift a little. Gravity assists often use moons and planets together. A carefully planned flyby can borrow a little energy from a planet's motion and reshape a spacecraft's trajectory, like a gentle sling that changes direction without burning much fuel. This slingshot idea is one reason missions can reach the outer solar system at all, using geometry instead of force. With that in mind, radar can look through haze and sometimes through ice. It can bounce signals off hidden surfaces and return an outline of shape and texture, even when a moon's atmosphere is thick or the light is dim. Titan mapping used radar to reveal dark lakes and dune fields, translating invisible echoes into quiet maps. Here's a calm surprise. Spectrometers read surfaces by color beyond our eyes. Molecules absorb and reflect specific wavelengths, leaving a fingerprint in the light that instruments can decode. Those absorption bands can identify water ice, salts, organics, and more, like recognizing a song from a few repeated notes. Slowly we notice future missions aim to revisit ocean moons. Closer measurements can test whether oceans are truly present, how thick the ice is, and what chemistry might be moving below. Plans often include repeated flybys and detailed sensing, radar for structure, spectrometers for composition, and particle analyzers for anything venting into space. And for one sleepy soul, that's enough to rest. A quiet fact: a moon's orbit can be measured by tiny timing shifts. When a spacecraft sends radio signals back to Earth, slight changes in the signal can reveal subtle changes in speed, which in turn reveal gravity variations. Those variations can map where mass is concentrated, sometimes hinting at denser rock, lighter ice, or even hidden layers. One more gentle truth: craters can reveal surface age by counting density. In general, more craters suggests an older surface, because it has had longer to be hit and marked. It's not an exact clock, but it's a calm comparison method, like comparing how scratched two stones are after different lengths of time on a rough path. In the background, some moons may have cryovolcanoes, ice lava. Instead of molten rock, mixtures of water, ammonia, or other volatiles can erupt in the deep cold, flowing and refreezing across the surface. The temperatures are far below freezing by Earth standards, and yet the same idea holds. Something warm inside finds a path outward, a small step forward. Moons can create auroras indirectly. In strong magnetic systems like Jupiter's, interactions between a moon and the planet's magnetic field can leave bright footprints near the planet's poles. These auroral signatures are like glowing notes in a larger magnetic song, tracing where energy is moving through space. A softer detail: rings and moons exchange material constantly. Micrometeoroids strike ring particles and moon surfaces, lofting dust that can migrate and resettle grain by grain. It's a slow recycling process, not like Earth's fast weather, but persistent in its own quiet way, just for a moment. The solar system's moons are a library of different worlds. In one collection you can find blazing volcanism, thick atmospheres, hidden oceans, cratered archives, and rings shaped by tiny shepherds. The sizes range from 1 kilometer fragments to more than 5,000 kilometers giants, like shelves holding everything from pebbles to planets. And for one sleepy soul, that's enough to rest. Farther out, exomoons may exist around planets in other systems. Detecting them is difficult in them because the signals they create in starlight are extremely small, like tiny extra ripples in a transit. Even so, the idea is steady and reasonable. If moons are common here, they may be common elsewhere too. Closer in. The idea of an exomoon expands what moon can mean. It reminds us that our solar system is just one arrangement among many, and that other stars may host families we haven't met yet. With billions of stars in our galaxy alone, the possibilities stretch outward like a quiet horizon if you drift a little. Moons show that companionship is common in space. Many planets keep not just one moon, but several, sometimes dozens, moving together in patient rhythms. In a calm way, it suggests that gravity rarely builds a world in isolation, and for one sleepy soul, that's enough to rest. With that in mind, tonight's moons can settle into a single quiet image, small circles moving steadily in the dark, repeating their paths without hurry. Their orbits can be measured in hours or in years, but the feeling of the motion stays the same, slow, reliable, and soft. Here's a calm surprise. The most relaxing fact may be the simplest one. Gravity is gentle, and it keeps time patiently, using the same rule across the entire solar system. The same pull that shapes a crater and steadies a ring can also guide a moon around a planet for billions of years. Slowly, we notice. A moon is a reminder that motion can be peaceful. Even constant movement can feel still. when it repeats in a calm pattern you can trust. The paths continue quietly, long after any one night has passed, and for one sleepy soul, that's enough to rest. And now you can let the whole journey soften into a quiet blur, the way distant lights soften when your eyes grow heavy, tides rising and falling on earth, not with urgency but with a steady rhythm that doesn't ask anything from you. Ice cracking and refreezing on Europa, lines crossing lines like gentle handwriting in pale stone. Ring light around Saturn, thin and bright, shaped by tiny moons that pass again and again, leaving ripples you could almost imagine as slow music. Hidden oceans under dark ice, warmed by motion, stirred by chemistry, existing without any sunlight at all. Distant captures, worlds that arrived late moving backward, still held by gravity like a quiet decision made long ago. Quiet craters keeping their memories not to burden anyone, just to remain. And gentle gravity itself everywhere doing the same patient work, holding, guiding, smoothing and turning the universe into a place of repeating patterns. You don't need to remember any of this. You can let the names drift away first, and then the numbers, and then even the images, until there's only the feeling of slow orbits and soft distance. If you're still awake, you can take one more easy breath in and a long, unhurried breath out. And if sleep is already close, you have full permission to follow it. Good night, and may your rest be deep and quiet. And if you ever want another calm walk through science in the dark, there will be another gentle story waiting for you. A quiet fact. A moon's orbit sits inside something called a Hill sphere. That's the region around a planet where the planet's gravity dominates over the sun's tug for keeping satellites. For the giant planets, that sphere is enormous, which is one reason they can hold on to so many moons, even very far out. One more gentle truth. A moon can have a faint exosphere instead of a real atmosphere. An exosphere is so thin that particles rarely collide, more like a light mist of individual molecules hopping along. Our moon has a very thin exosphere, and some icy moons can have similar ghostly layers made by sunlight and impacts. In the background, micrometeorites can kick atoms off a moon's surface. This process is called sputtering, and it's like a constant gentle sandblasting by tiny particles and charged ions. Over time, sputtering can feed a thin cloud around a moon and subtly change the chemistry of the outermost surface. A small step forward, some moons glow faintly in ultraviolet because of their tenuous gases. When particles get excited by sunlight or magnetospheric bombardment, they can emit light at specific wavelengths. It's not a bright glow like a lamp, more like a whisper of light that only sensitive instruments can see. A softer detail. Moons can have libration, a gentle wobble in how they appear from their planet. Even when a moon is tidally locked, small variations in its orbit and tilt can let a viewer see a bit more than half of its surface over time. For Earth's moon, libration lets us peek at about 59% of the lunar surface across many nights. Just for a moment, even a wobble can feel like calm proof of motion. A locked face still shifts slightly, like a slow nod that repeats without hurry, and for one sleepy soul that's enough to rest. Farther out. Crater saturation can happen on very old surfaces. That's when impacts become so common over the billions of years that new craters overlap old ones, filling the surface with circles upon circles. On a saturated world, the landscape looks like it has run out of blank space. Closer in, some moons show bright rays that fade with space weathering. Radiation and micrometeorites slowly darken fresh material, so a bright crater can look young compared to its neighbours. The fading can take millions to tens of millions of years, depending on the environment, if you drift a little. A moon's density tells a simple story about rock and ice. Rocky moons tend to be denser, while ice-rich moons are lighter, like the difference between stone and packed snow. When scientists measure density from mass and size, they're quietly measuring the ingredients. With that in mind, Io's extreme volcanism is tied to how strongly it's flexed. The tidal bulge inside Io can rise and fall by tens to even over 100 meters, depending on models and assumptions. That constant kneading is like bending a paperclip again and again, except the paperclip is a world. Here's a calm surprise: volcanic plumes on Io can rise far above the surface. Some observed plumes reach hundreds of kilometers high, tall enough to feel enormous compared to the moon's own size. In the darkness near Jupiter, those plumes are brief fountains of material returning softly to the ground. Slowly we notice Europa's surface has fewer tall mountains than Earth. Ice behaves differently than rock, and in Europa's low gravity, the surface tends to break and shift in plates rather than building towering peaks. Many of Europa's most striking features are lines, ridges, and bands, flat, wide structures written across ice. And for one sleepy soul, that's enough to rest. A quiet fact: Europa's surface ice is bombarded by Jupiter's radiation. That bombardment can split water molecules and create compounds like hydrogen peroxide and oxygen-bearing materials. It's a kind of chemistry powered by particles, happening on a world that is otherwise quiet and cold. One more gentle truth: oxygen can exist around Europa in an extremely thin form. It's not breathable air, just a sparse cloud of molecules that come and go. Think of it as the delicate halo, more like a trace than an atmosphere. In the background, Ganymede's auroral behavior helped reveal its internal layers. When its auroras shift in response to Jupiter's magnetic field, the motion can hint at conductive layers inside, like a salty ocean. It's a gentle detective story told through invisible fields, a small step forward. Ganymede's size makes it feel like a planet that happens to orbit a planet. At about 5,268 kilometers across, it would be the 9th largest object in the solar system if it orbited the Sun directly. Yet it stays as a moon, held in Jupiter's gravity like a large companion, a softer detail. Callisto's distance gives it a quieter tidal life. With less stretching, the interior may have cooled more, leaving fewer reasons for the surface to be replaced. That's part of why Callisto's craters remain so sharply preserved. Just for a moment, an ancient surface can be restful to imagine. It's a place where time passes without rushing, keeping its marks the way stone keeps fingerprints. And for one sleepy soul, that's enough to rest. Farther out, Saturn's rings have subtle colour differences across their bands. Some regions look slightly more clean ice, while others contain more dust and darker contamination. Even when the overall ring looks bright, tiny differences in composition can tint the light. Closer in, some ring moons act like moving sculptors. A small moon's gravity can raise waves, carve edges, and maintain gaps with repeated passes. It's not one dramatic push, it's the same small pull applied over and over, if you drift a little. Prometheus and Pandora help shape Saturn's F-ring. Their gravitational nudges keep the ring narrow and dynamic, creating knots and streamers that shift over time. The F-ring itself is thin and braided, like a delicate thread that refuses to settle. With that in mind, some moons share an orbit in a gentle exchange. Janus and Epimetheus, for example, move in nearly the same orbital zone and swap positions in a slow dance as they pass each other. The exchange happens on a timescale of years, like two quiet walkers trading lanes without colliding. Here's a calm surprise: Enceladus is small, but its influence is enormous. The E-ring it feeds spans a huge region of space compared to the Moon's 504-kilometre diameter. A tiny world can seed a vast halo simply by venting a little water and ice. Slowly we notice some plume particles from Enceladus escape and some fall back like fine snow. In low gravity, grains can arc outward and return gently, dusting the surface with fresh frost. That constant light snowfall can help keep parts of the surface bright, and for one sleepy soul, that's enough to rest. A quiet fact. Titan's thick haze is produced high in the atmosphere. Sunlight breaks methane and nitrogen apart, and the fragments recombine into complex organic molecules that clump into tiny particles. Those particles drift downward over time, like a slow planet-wide snowfall of chemistry. One more gentle truth. Titan's lakes sit mostly near the poles. The distribution hints at a climate pattern, with methane more likely to condense and collect in colder regions. Some seas are hundreds of kilometers across, dark and smooth under a dim sky in the background. Titan's surface gravity is gentle compared to Earth's. It's about 1.35 meters per second squared, roughly 14% of Earth's gravity. That softness changes how winds move grains and how rain falls. Slower, lighter, and calmer, a small step forward. On Titan, water ice behaves like bedrock. At around minus 179 degrees Celsius, water is hard and strong, so mountains and ground can be made of ice as if it were stone. Meanwhile, methane can play the role of water, flowing and pooling in the places. A softer detail. Some moons show cryovolcanic hints that are still debated. Scientists look for smooth flows, unusual domes, and signs of resurfacing that might come from cold eruptions of water mixtures. The calm truth is that evidence can be subtle, and interpretation takes time and careful measurement. Just for a moment, debate in science can be soothing in its own way. It means the story is still unfolding gently with room for patience. And for one sleepy soul, that's enough to rest. Farther out, Iapetus's ridge runs along part of its equator. This ridge rises like a long spine, and its origin is still discussed, with ideas including ancient ring debris or internal processes. In places, it reaches heights of many kilometers, tall enough to cast long shadows in low sunlight. Closer in, Mimas's giant crater shows how close a moon can come to breaking. A large impact on a small body can fracture the interior and leave lasting structural weakness. Yet Mimas stayed intact, a reminder that survival in space can be as much about luck as it is about strength. If you drift a little. Rhea, Diante and Tethys each show a different balance of old and new. Some are heavily cratered, some show bright fractures, and some have long canyons that suggest stress in their icy crusts. Even within one planet's moon family, there's a quiet variety. With that in mind, Trojan moons sit at stable gravitational points. The L4 and L5 points are places where the pulls of a planet and a larger moon balance in a way that can hold smaller bodies. It's like a gentle pocket in the flow where a small moon can rest while still moving. Here's a calm surprise. Uranus's tilted system makes its seasons unusual. As Uranus circles the Sun, its poles can point toward or away from sunlight for long stretches, changing how its moons are lit over time. The geometry is slow and strange, like a lamp turning sideways as it moves. Slowly we notice. Miranda's patchwork terrain suggests a complicated past. Some regions look like they were uplifted and rearranged, with abrupt borders between landscapes. Even with limited close-up data, Miranda feels like a moon that experienced deep internal change and then went quiet again. And for one sleepy soul, that's enough to rest. a quiet fact. Neptune's rings are faint and sometimes clumpy. Instead of uniform bands, some arcs appear brighter in certain regions, as if ring material gathers into partial segments. Those arcs can be maintained by gravitational interactions and resonances, making them a delicate structure that requires balance. One more gentle truth. Triton's retrograde orbit hints at a Kuiper belt origin. Capture would bring Triton in from the outer solar system where many icy bodies travel. That kind of arrival can change the entire neighborhood, like a new, heavy object entering a calm pond and shifting the ripples. In the background, Triton's surface shows a mix of textures and terrains. Some areas look smooth, some look ridged or pitted, and some show dark streaks that suggest seasonal changes. In the deep cold, weather can still exist, just in slow motion with different materials. A small step forward. Seasonal sunlight on distant moons can move volatile ices. Nitrogen, methane, and carbon monoxide can freeze and sublimate depending on temperature. That means a world can breathe frost from one region to another over years, even where the sun is a small pale light, a softer detail. Phobos' close orbit makes it a fast companion. At about 7.7 hours per orbit, it races around Mars so quickly that it can rise in the west and set in the east on the Martian sky. Speed, even in silence, can be startling, just for a moment. Deimos moves more slowly and more distantly. Its calmer orbit at about 30.3 hours feels like a quiet watch, circling at a respectful distance, and for one sleepy soul, that's enough to rest. Farther out, Pluto and Charon's binary nature affects the smaller moon spins. In that gravitational environment, tiny moons can tumble and rotate with complex patterns rather than settling into a neat lock. Their motion looks like gentle confusion, still lawful, still gravitational, but less predictable. Closer in. Haumea's rapid rotation shows how shape can follow spin. When a body spins fast enough, it stretches into an elongated form, an equilibrium between gravity pulling inward and rotation pulling outward. At about 3.9 hours per rotation, Haumea is a quiet example of that balance, if you drift a little. Eris and Dysnomia remind us that companions exist far beyond Neptune. Even in the dim Kuiper belt and beyond, small systems can stay bound for long spans. Distance doesn't stop gravity, it just makes everything slower. With that in mind, across the solar system, moons are a lesson in scale. Some are smaller than a city and some are larger than planets, and yet all follow the same calm rule. The path you take depends on the mass you carry and the space you move through. It's a gentle kind of fairness in physics. Here's a calm surprise. Even the quietest moon is still moving. It's turning, orbiting, drifting through sunlight and shadow, repeating the same path until the night feels familiar again. Motion can be steady enough to feel like stillness, and for one sleepy soul that's enough to rest. A quiet fact. The moon has mass scones, or mass concentrations hidden under some basins. These are regions where dense material lies beneath the surface, often linked to ancient impacts and later lava fill. Spacecraft tracking revealed them because the moon's gravity tugs a little more strongly in those places, like a subtle hand pulling on an orbit. One more gentle truth. Mascons can slightly nudge a spacecraft's path. When a probe passes over a denser region, it speeds up by a tiny amount, then slows again as it leaves. These changes are small but measurable, and they help scientists map what's under the lunar surface without digging. In the background, the moon's far side holds one of the largest impact basins in the solar system. The South Pole Aitken Basin stretches for thousands of kilometers, a scar so wide it reshaped the crust itself. It's a reminder that impacts can be planet-scale events, leaving quiet marks that persist for billions of years. A small step forward, Some lunar craters have central peaks. After a big impact, the ground can rebound upward, like a slow splash in rock, forming a peak in the center. These peaks can rise hundreds of meters to a few kilometers, depending on crater size, like a mountain lifted from the floor of a bowl. A softer detail. Impact melt can flow like a brief lava. The shock of an impact can liquefy rock, and that melt can pool and spread before freezing. It cools into smooth sheets that look different from the surrounding rough terrain, like glassy patches left behind after a violent moment. Just for a moment. The moon's surface is quiet now, but it remembers when it wasn't. The calm we see is what remains after the heat, and impacts faded into deep time, and for one sleepy soul, that's enough to rest. Farther out, some crater rims cast shadows that last a long time. Near the poles, low sun angles make shadows stretch for kilometers across the ground. In those long shadows, temperatures can stay lower, and the landscape looks like a soft black and silver relief. Closer in, the moon has regions called swirls, faint bright patterns on the surface. These swirls are often linked to magnetic anomalies, patchy magnetism in the crust that can deflect the solar wind a little. The result can be a brighter surface that weathers differently, like pale brush strokes that stay cleaner, if you drift a little. Magnetic anomalies on the moon are small and local. The moon doesn't have a strong global magnetic field like Earth, but certain patches of crust hold magnetized rock. Those patches are like quiet compass points frozen into stone, remnants of an earlier era. With that in mind, lunar dust can become electrostatically charged. Sunlight and the solar wind can give dust grains electric charges, which can make them cling and sometimes even loft slightly above the surface. It's not a storm like on Earth, more a gentle, ghostly movement that may happen near sunrise and sunset lines. Here's a calm surprise. The boundary between lunar day and night is called the terminator. It's the line where sunlight ends and darkness begins, and it moves slowly across the surface as the moon rotates. Near that line, shadows are longest and small bumps look dramatic, like quiet sculpture revealed by low light. Slowly we notice a moon's brightness is measured by albedo. A high albedo surface reflects more light, like fresh snow. A low albedo surface absorbs more, like charcoal. Many icy moons are bright, while some captured or dust-coated moons are dark. And the difference changes how warm they get in sunlight. And for one sleepy soul, that's enough to rest. A quiet fact. Thermal inertia describes how fast a surface heats and cools. Dusty regolith tends to warm and chill quickly, while solid rock holds heat longer. This is one reason airless moons can have sharp temperature swings, especially when the surface layer is a loose insulating powder. One more gentle truth. Some moons have fresh, young-looking craters with crisp edges. Sharp rims and bright ejecta suggest relatively recent impacts. Over time, micrometeorites soften edges and darken bright material, so a crisp crater can feel like a new mark in an old book. In the background, a moon's orbit can precess, meaning it slowly rotates its orientation in space. The tilt and shape of an orbit can change over time due to gravitational tugs. These cycles can take years to thousands of years, like a slow turning of an invisible dial. A small step forward. Inclination is how tilted a moon's orbit is compared to a planet's equator. Regular moons often stay near the equatorial plane with low inclinations. Irregular moons can have high inclinations, sometimes well above 30 degrees, showing that their histories were less orderly. A softer detail. Some moons orbit close to the edge of stability. Far from a planet, the sun's gravity becomes more influential, and distant moon orbits can be easier to disturb. That's one reason the autonomous moons are often irregular and captured, held, but in looser, more delicate patterns, just for a moment. Stability in space is rarely absolute. It's a gentle balance. A moon can be held for billions of years simply because the forces line up quietly enough, and for one sleepy soul that's enough to rest. Farther out, Jupiter has tiny inner moons embedded near its faint rings. Moons like Mtiti and Drostea orbit very close to Jupiter, in regions shaped by intense gravity and radiation. Their orbits are fast, on the order of hours, circling so close that they live in constant particle weather. Closer in, some of Jupiter's inner moons help supply ring dust. Micrometeoroid impacts can knock off tiny grains that spread into faint rings. The ring can be thin and dim, but it's a real structure, kept alive by repeated small impacts, not by one dramatic event. If you drift a little, Amalthea is an inner Jovian moon with a surprisingly low density. Its size is on the order of a couple hundred kilometers across, yet its density suggests a porous interior, like a loose pile of material rather than a solid rock. In Jupiter's strong gravity, even a rubble-like moon can survive in a stable orbit. With that in mind, Io's volcanic heat can create changes that happen quickly by geological standards. Some lava flows and surface deposits can shift over months to years, not just over eons. It's one of the rare places where recent activity in the outer solar system can mean within a human lifetime. Here's a calm surprise. Europa's surface has bands that look like they pulled apart and refroze. In some areas, the terrain resembles spreading centres, where two sides drifted slightly and new ice filled the gap. The distances can be kilometres wide, like a slow seam opening and closing. Slowly we notice Ganymede's magnetic environment is complex because it sits inside Jupiter's magnetic field. That means Ganymede's own field interacts with a larger one, creating shifting patterns in charged particles. It's like a small bubble of magnetism moving through a larger ocean of magnetism. And for one sleepy soul, that's enough to rest. A quiet fact: auroras can appear as faint ultraviolet glows on some moons. These emissions are caused by energetic particles striking thinnesses and exciting atoms or molecules. The glow is not something a human eye would see easily, but instruments can detect it like a quiet signature of invisible activity. One more gentle truth: some moons have induced magnetism rather than their own magnetic engine. A salty ocean can respond to a changing external magnetic field by generating currents, which then create a secondary magnetic signal. This is why ocean moon science often sounds like detective work. It reads invisible clues. In the background, Saturn's rings contain gaps that match orbital resonances. In these regions, the repeated timing of a moon's gravity can clear out particles. The Cassini division, for example, is shaped by resonances and complex ring dynamics, a broad dark gap that's still not completely empty. A small step forward, Saturn's a ring contains the Encke gap and the Keeler gap. These are narrow lanes cleared and maintained by small moons and resonant effects. Even in a ring made of countless particles, a small orbiting body can carve a clear path. A softer detail: Atlas is a small moon near Saturn's rings with the smoother, flying saucer shape. It likely collects fine ring material around its equator, building a soft ridge. This is gravity working on dust, slowly gathering particles into a gentle belt. Just for a moment, a moon collecting dust is a quiet image. Grain by grain, space builds a shape without hurry, as if time itself is doing the sculpting. And for one sleepy soul, that's enough to rest. Farther out, Uranus has small moons that shepherd its rings. Moons like Cordelia and Ophelia are associated with the edges of Uranus's rings, helping maintain narrow structures. Their influence is subtle but steady, small bodies doing long-term housekeeping. Closer in. Uranus's major moons were mostly seen closely only once. Voyager 2 provided the best detailed images in 1986, and much of our knowledge still rests on that single passage. It's a calm reminder that exploration can be brief, and understanding can take decades afterward, if you drift a little. Neptune's moon. Nereid has a very eccentric orbit. Its distance from Neptune changes greatly as it goes around, which is unusual compared to many regular moons. That eccentricity fits the idea of a disturbed system after Triton's capture, with some moons left in altered paths with that in mind. Proteus is one of Neptune's larger inner moons and is irregular in shape. It's heavily cratered and dark, a quiet, lumpy world that still holds close to Neptune. Even larger moons can remain unsmoothed if they're not quite big enough for gravity to round them fully. Here's a calm surprise. Triton's surface likely changes with seasons as nitrogen frost moves. As sunlight shifts, nitrogen can sublimate from one region and freeze onto another. This slow migration can create new bright frost, dark exposures, and changing patterns over years, like a planet-wide breathing of ice. Slowly we notice cold worlds can still have weather, just made of different bond materials. Instead of water rain, you can have methane rain. Instead of water ice shifting, you can have nitrogen frost moving. The pattern stays familiar even when the ingredients change, and for one sleepy soul that's enough to rest. A quiet fact. Many Kuiper belt objects have moons, suggesting collisions and captures are common out there too. The distances are vast, and the sunlight is dim, but gravity still organizes pairs. Orbits can take days to weeks, moving in a quiet slow circle into the outer dark. One more gentle truth. Some moon systems form from mutual capture during close encounters. If two bodies pass close enough and lose energy, sometimes with help from a third body or debris, they can become bound. Capture is rare in any single moment, but over billions of years, rare events still happen in the background. Transit timing variations are one method scientists consider for detecting exomoons. If a planet's transit across its star shifts slightly in time from orbit to orbit, a moon could be one possible cause. The signals are tiny, which is why exomoon detection remains difficult and careful. A small step forward. The calm mathematics of orbits works the same everywhere. Whether it's a tiny moon around an asteroid or a massive moon around a giant planet, the basic rule stays. Farther orbits take longer, closer orbits move faster. It's a gentle pattern and you can almost feel, even without remembering the numbers, a softer detail. In our own night sky, the moon's slow motion can be seen over a single evening. In an hour, it moves about its own width across the background stars, though the stars are usually washed out in city light. That steady movement is a simple visible proof that even familiar things are always drifting, just for a moment. The moon doesn't rush and it doesn't pause, it just continues, keeping time in the quietest way by moving. And for one's sleepy soul, that's enough to rest. Farther out. Across the solar system, moons are often the best places to find extremes. The coldest traps, the strangest spins, the thickest moon atmosphere, the most active volcanism. All of these can live on moons rather than planets. Moons are small enough to be shaped quickly, and old enough to carry long memory. Closer in, and if you're awake, you can let these last details fade into a soft background hum. The names can blur first, then the measurements, until only the sense of slow circling remains, small worlds repeating their paths held by gravity in the dark. If you drift a little, you can imagine a ring edge, a plume, a crater rim in shadow, and then let it dissolve. Another orbit completes somewhere far away, and nothing needs your attention that in mind, the night can hold all of it for you. The moons will keep turning whether you remember them or not, and the universe will keep its calm, steady rhythm. Good night, have good dreams.